Hello and welcome to another video. We're going to be talking about the characterization of the norm of quadratic extensions. So I have taken the liberty of writing the definition up here. So we define the norm nu of some element of a quadratic extension on integers as a plus b times the square root of s, and we map it onto the absolute value of a squared minus s times b squared. Okay. Now, we claim that this norm, thus defined, has three properties. One, that in a way it is linear with respect to the dot operation, that nu of u is equal to 1 if and only if that element is invertible, and that if u divides v but v doesn't divide u, which it's pretty common, I think, then the norm of u divides the norm of v, and they are not equal at the same time. This is used often as a necessary condition, because from this it follows that nu of a not dividing nu of b implies that a does not divide b. So if we want to find out if two elements of a quadratic extension divide each other, this is a quick way of finding out if they don't. They might, but if this is true, then yeah. Now the proof. 1. By direct computation. So nu of u times v is equal to dot 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 nu of u times nu of v is equal to dot dot dot. We would find out it is the same thing. It would require some nasty computations, which are completely mindless, by the way, so we're not going to do it. So trivial. All right, now this onto the second claim. That one's more interesting. We shall denote u to be some a plus b times the square root of s. If nu of u, which is of course the nu of a plus b times the square root of s, is equal to 1, well, I mean, this by definition is also equal to a squared plus s times b squared is equal to 1, then a squared minus s times b squared is equal to, now we are simply removing the absolute value, but this is equal to the following factorization. So they have a plus square root of s times a minus b times the square root of s, and this must be equal to plus minus 1 because we remove the absolute value, and thus u inverse is equal to plus minus a minus b times the square root of s. Right, well, here is our u, and here we have our u inverse. Right, so we have proven one implication. So this was the left to right implication. Now let's have a look at the right to left, because we are proving an equivalence. There is a biconditional. If some u times v is equal to 1, then by the claim 1, which I sort of didn't prove, but not really, then by this it holds that 1 is equal to nu of 1, which is equal to nu of u times v, which is equal to u times, of nu times u times nu of v, and thus we have nu of u is equal to nu of v is equal to 1, because u and v are both integers, and the norms are also integers. Right. All right. Number 3. All right, so assume Assume that U divides V and that V does not divide U. So the first condition, we have that V is equal to sum U times W, and thus by the claim number 1, we have that nu of V is equal to nu of, or the norm of U times the norm of W, and thus norm of V divides norm of U. Of course, the other way around. Norm of U divides the norm of V. Suppose they were equal. Right, we are trying to show that they are not equal. So suppose for contradiction that they are. What then? And in order for this equality to be preserved, then needfully nu of W is equal to 1. Right. But then by claim number 2, W is invertible. Because that's, mind you, precisely what claim number 2 says, that the norm of any element is 1 if and only if it is invertible. Hence, W is invertible. But then we can write that U is equal to V times W inverse, right, from up here. Thus, V divides U at the same time, and by assumption, V does not divide W, which is a contradiction, and this concludes the proof.